Hello everyone, let's go through assignment number 10. In the first question, we have several relations, each for one item, and these relations are defined on this set. This set contains 4 elements, 1, 2, 3, 4. This is one way to define relation. It is also possible to define relations using, for example, Cartesian product. Like, for example, I say set A is 1, 2, 3, 4, set B is 1, 2, then A multiply B could be a relation itself, right? Because you can define it as pairs, as you can see in the items. So this is just one way to represent relations without even mentioning about the set which these pairs are based on those elements. And you can also see that in different examples. And we can simply define it, as I said, just by Cartesian product, for example. And you should know about sets very well in order to solve questions related to relations. Of course, this topic is very easy, but students tend to lose points because they underestimate sets, and this could be very painful to lose points just because of such easy questions. So please pay attention to the way we go through these properties of relations, and in the final exam hopefully you will be careful not to rush in order to give the final answer, because it doesn't take that much time to know, for example, a set is, for example, symmetric or transitive, and so on. Okay, so let's go through question number 1. In this question, we asked you to check whether these relations are reflexive, symmetric, antisymmetric, and transitive. It's possible to have all the properties, it's possible to have some of them, it's possible also to have none of them. So one by one we check for these properties for each item. For item A, let's check reflexive. When we talk about reflexive, it means that search for the elements inside this pairs. Do you see, for example, if you see 2, it means that for sure I should have 2, 2 as well. For example, if I have 2, 3, I should have 2, 2 for sure. If I have 3, it means that I should have 3, 3 for sure. Otherwise, this is not a reflexive relation. So I see 4 elements here. Even in the second component doesn't matter, because it shows that this is one element in the pair. And you will see that we don't have 4, 4 here. So item A is not reflexive. These solutions are provided by student. I checked it. I think it should be okay. It should be okay, but we are now practicing together from the scratch. So for part B, I see 1. I see also 1, 1. I see 2. I see also 2, 2. 3, 3, and 4, 4 are also there. So this one should be reflexive. This is okay. This is reflexive. Part C. I don't see 2, 2, and 4, 4. Even if one of them were missing, then if one of them was missing, then you would say, for example, this set is not reflexive. So this is for sure not reflexive. I have 1, 2. I don't have 1, 1. So this is not reflexive. For part E, we can see that the first element and the second element are exactly the same. It doesn't matter. Still, this is reflexive, because each element that you can see that the second component also, you see, is equal. It's already there. We have a pair with the same element for the first and second component. So yes, part E is reflexive. 1, 3 is here, but do we have 1, 1? No, we don't have. If we have 1, 1 and we don't have 3, 3, still we would say F is not reflexive. Okay, so as you can see, to check whether these sets have a property or not, I'm looking for a counterexample. If I find it, then right away I would say this property doesn't hold for this set. If you cannot find any counterexample, then you say by saying about the definition that why this is reflexive. Okay, didn't find the counterexample is not a proof. To say that, for example, this set, for example, part B, is reflexive, it means that you should rewrite the definition of a reflexive set to say that for all the elements I found in this set, this relation, then I could find a pair which first and second component were the same. So in order to write a complete solution for such questions, if you find a counterexample, you say, okay, this set is not reflexive, this relation is not reflexive because we didn't find, we found the counterexample, and this is the counterexample. Mention about the counterexample. For example, here for part F, I see 1, 3, so I should also observe 1, 1 as an element in this relation, but I don't find it. So this is a counterexample. This is a counterexample. But if you know, for example, relation B is reflexive, then you should rewrite the definition of a reflexive relation and say because of this reason this is reflexive. I think this is clear now. Now let's go through other properties. Symmetric. In the symmetric case, it means that when first component, let's call, for example, A first component, B second component. If AB is there as an element inside that relation, then BA should be there too. Otherwise, this is not symmetric. So for example, 2, 3 is here, then 3, 2 should be there. It's okay. But here 2, 4 is here, then 4, 2 should be here too. Otherwise, this is not symmetric. So you found a counterexample. And because of that, you would say relation A is not symmetric. For item B, this is symmetric. Why is that? Because 1, 2 is here, 2, 1 is here, 1, 1 and 1, 1 are the same, so you write them in sets the same. Relation is a type of set, so it obeys the rules of set. The order doesn't matter. Like the order of first component and second component matters because each one of them are elements. But the order of elements doesn't matter. Like if I write here 2, 2 here, or first before 1, 1, doesn't matter, right? Okay. So 1, 2 is different from 2, 1 as an element. But if you change the position of both of elements together, then it's okay. All right. This is symmetric because I couldn't find a counterexample. Then I should write the reason. The reason is that the definition of symmetric. Because for all pairs of AB, I could find BA. And that's why this is a symmetric relation. Because didn't find the counterexample alone is not the proof. Okay, what about this one? Yeah, this relation only has 2 elements, but doesn't matter. As you can see, it shows that this is symmetric. 2, 4 is there, 4, 2 is here, then it's okay. Next one, 1, 2 is here. You found a counterexample. 2, 1 is not here. So D is not symmetric. What about E? Yes, 1, 1 is here. Then another 1, 1 could be here, but we write it only once. So that's good. So again, this is a specific case, then this is symmetric again. For part F, 1, 3 is here, 3, 1 is here, no problem. 1, 4 is here, 4, 1 is not inside the relation. So this F is not symmetric. So I think the idea about symmetric property is clear. What about antisymmetric? It means that whenever you have AB, you shouldn't have BA. Otherwise, A and B are equal. It means that part E could be antisymmetric. It's okay. Because it's true that 1, 1 is here, and again another 1, 1 is here. AB and BA in a particular case is here, but both of them are equal, both of the components. So part E is antisymmetric. But let's see, for part A, 2, 3 is here, 3, 2 is also here. This is not antisymmetric. You see, there's a counterexample. For part B, here also you can see that 1, 2 is here, 2, 1 is also here. This is not antisymmetric. Again, we can say the same about C, even it has 2 elements, but 2, 4 is here, 4, 2 is here. This is antisymmetric. This is not antisymmetric because this is symmetric in this case, but not antisymmetric. You found the counterexample. Part D, 1, 2 is here, 2, 1 is not here. It's okay. 2, 3 is here, 3, 2 is not here. It's okay. 3, 4 is here, 4, 3 is not here. This is antisymmetric. And this one, you should say, for example, based on the definition of antisymmetric, that for all AB, I couldn't find BA. And we can also mention about the case that we don't even have the same items, but not necessary. You don't even need to mention that because it's already obvious. Even if we had 1, 1 here inside this set, again, it was antisymmetric. You see, for example, for item E, all of them are the same, but they are antisymmetric. This is an exception for antisymmetric. We are allowed. If A and B are equal, this is okay. This is not a counterexample. And for part F, 1, 3 and 3, 1, this is a counterexample. So we cannot consider it an antisymmetric property for this relation. What I want you guys to notice is that it's possible that a relation is not antisymmetric and symmetric at the same time. It's also possible that both of them at the same time could be the properties of a set. So it's not like whenever you find symmetric, then you say for sure that set is not antisymmetric. And that's because of this exceptional case that when A and B are equal, then it's okay. So we should be careful about that. And about transitive, what about this property? This property says that if you have A, B, and C elements, then as pair when you define them as AB and BC, then if we have AB and BC as 2 pairs inside this set, AC should be also inside that set as well. So 2, 2 is here, so whenever you have the same, it's okay. You don't worry. But when we talk about AB and BC, it means that 2 pairs at the same time should be checked with each other. So we don't just move on. 2 by 2 we check. So when you have 2, 2, I check the second component. This second component, does it have any common value with the first component of any of these pairs? If this is the case, we should check it. 2, 2, this is 2 in the second component. In the first component of this pair and this pair, I found 2. So you see 3 and 4 are the second components of that. What does it mean? First component and second component of these 2. So 2, 3 and 2, 4 should be inside this relation as well. And they are. You see 2, 3 and 2, 4, they are. So it's okay. I move on to the next one. 2, 3. The second component is 3. Then I look which one of these pairs have 3 as the first component. These 3, you see? So the first component, second component of these pairs. 2, 2. Is it here? Yes. 2, 3. Is it here? Yes. 2, 4. Yeah, this is here. Great. So we move on. 2, 4. I don't have any pairs which start with 4. Then I can stop right here. We have checked everything. This set, this relation is transitive. This is okay. Next one. Let's give you a counter example. I think you got the idea. Let's give you a counter example, like part D. 1, 2. So I check these pairs that which one of them contains 2 as the first element. So this is A, this is B, this is B, this is C. I'm looking for AC at the end. So A2, 2, 3. Now I should find out whether A1, 3 is already in the set or not. I don't see any 1, 3 as a pair. This is a counter example. So part D is not transitive. Let me give you another counter example like in part F. So 1, 3, I check which ones have 3 as the first component. 3, 1 and 3, 4. Okay. So 1, 3, 3, 1. So 1, 1 should be inside the set, but it's not. So as soon as you find one counter example, it's good enough to say this relation doesn't contain, it's not transitive. But whenever this is transitive, then again, you should give the definition and explain why this is the case. Just saying that we didn't find counter example is not a good enough solution. Okay, this was related to question number 1. I think this is pretty clear. For question number 2, we have already practiced with this one. So I don't need to go through the details that much. What I want to say is about the things we should be careful about such questions. So these are compositions questions. Like we define a relation or we define several relations, then we ask about their compositions. We already practiced it in our lecture, both for different relations and also for the same relation like this. Whenever you see power on relations, it means that we are talking about the compositions, not the Cartesian product. We should be careful. R power 2 is not R multiply R. This is R composite R. Okay? We should be careful about it, and we discuss about it in details in our lecture. So, one way to define relations, as I said, is to mention about the set and define pairs as elements of relation. So these elements as pairs are already given to you as R. And sometimes I would say the multiplication of two different sets and define it as R, so you should know how to calculate these things. So the operations in sets are important. We practice it in the midterm, that if we apply different operations like A union B, how do you find out the final answer? So I can define, for example, R is equal A union B. Now find R power 2. And R power 2, it means that we are talking about the composition, not the power, not R multiply R. So these things we should be careful about. And another thing is that when you see R5 and you continue, for example, R2, find out what's R2, what is R3, what is R4, and none of them are equal to each other, you don't find any trend, then we have no other choice to also calculate R5. But sometimes, as I mentioned in the lecture, you would notice that R3 and R2 are exactly equal. They have exactly the same elements. So if that's the case, then R4 and R5, all of them will be equal to R2 and R3 as well. So whenever you find the trend, then you would say R4 and R5 are equal to R3 and R2, so you don't need to calculate any longer. But if there is no equality between them, then you need to calculate until R5. I didn't check whether these calculations are correct or not, but that's the thing that you should take into the account, so that avoid wasting time if you find out that you can't find the trend. Okay, guys, if you have any questions, please let me know. Otherwise, we will talk about our next lecture on Friday. And by the way, based on the decision of the department, we had to change the date of the final exam. Please check the announcement. It should be between 18th of January to 30. So they will announce it. And I will also announce it on our auto class as well. You keep checking your CET system so that you won't miss the date of the final exam. But anyway, the previous date that we announced is no longer valid. In CET, they called it midterm number 2, so it's no longer valid. And based on the suggestion of the department, we had to do it inside that period, and I also announced it in the announcement, and please check it out. Okay, guys, if you have any questions, please let me know.